We're going to use an algorithm called an autoencoder. This is the sort of neural network that we have been looking at, this funnel shape, right? And so this is the example where we were having a neural network receive MFCC analyses and then predict frequency modulation parameters. Our neural network looked something like this. Big input, small output, and a hidden layers that was somewhere in between to create the funnel. An autoencoder is shaped like this, in that we are going to have more inputs, some bottleneck in the middle here that is a smaller number of nodes, and then we're going to expand back out to the same number of outputs that we have as inputs. And that's because when we train the autoencoder, we're actually going to train this neural network to predict the exact same thing that it is receiving as input at the output layer. So we put in a vector as the input, and it will try to predict the exact same vector as the output. The reason why this is challenging for the neural network is because it has to do this prediction through this bottleneck layer. So essentially we're trying to have it, this is 10 or so inputs. We're trying to have it understand these 10 values in a two-dimensional space and be able to recreate the 10 values after positioning all of our data points in this two-dimensional space. Autoencoder, it encodes itself. Auto is the prefix for self, or the root for self. So it's trying to encode itself by taking the same input, predicting it to the same output. The autoencoder that we're going to look at here is going to take in this set of trombone tones. I'm going to remove the silence. And then I'm going to go every 2048 samples and save that as a data point that has 2048 dimensions. And that is going to be the input to the neural network that we're going to try to have it take as input and predict as output. Take in that wavetable of audio samples and then recreate that wavetable of audio samples. And so what we're going to try to do is train it to understand this space of audio samples that we are going to create. And then eventually we're going to use it to predict or create new wavetables based on these trombone tone wavetables, and hear how they sound. In order to do this, we're actually not going to feed the neural network a vector that is 2048 samples long. In order to have a vector that is that big, it would take a long time to train because we would need a very large neural network, a very large autoencoder structure to be able to do that. And so what we're going to do first is we're actually going to use PCA to reduce the number of dimensions from 2048 samples down to just 130 dimensions, the first 130 principal components of our data set. And then we're going to feed that 130 dimensional vector, or that 130 dimensional data set, into the autoencoder, which will have an input layer of 130, a hidden layer of 80, a hidden layer of 40, a hidden layer of 2, that is that bottleneck space there. And then we're going to expand back out to hidden layer of 40, hidden layer of 80, output layer of 130. And then from that output layer of 130, we're going to do an inverse PCA to go from the 130 values that the neural network gives us back into a 2048 sample wavetable. Now, one thing we'll notice is that going from 130 dimensions to 2048 dimensions is not really possible. The way that this inverse PCA works is it's going to do its best to recreate what might have been the original 2048 sample wavetable from these 130 values that are coming out of the neural network. And the reason why this actually can work pretty well is because the way PCA works, remember, is that it makes the lower ordered principal components, these first 130, are hopefully going to maintain most of the important information about how these original wavetables were related to each other, most of the important information about how these wavetables actually looked. And so when we do the inversion, even though we only have, a 20th or so of the number of dimensions, hopefully this smaller set of dimensions contains the important information that once we convert to the 2048 samples, they'll be pretty accurate. be pretty similar to what they were when we started. So, okay, I'm going to make the data set here and then print the data set. And now we can see that we have 1,052 rows. So 1,052 wavetables that all have 130 columns. And this is because here I'm doing the removing of the silences, and here I'm iterating over the buffer and extracting the wavetable, 2,048 samples, and then automatically doing the PCA transformation. So here's our 130 principal components for each of those wavetables, 1,052 of them. Now we can train the neural network and watch how the loss goes down. You can see my hidden layers here is 80, 42, 40, 80. And of course, the input layer is 130 and the output layer is 130. And when I tell the fluid MLPRegressor to fit, it is taking in slices PCA as the input data set and using slices PCA as the output data set. And so that's how we're using it as an autoencoder. We're telling it to make the same prediction as the output that it receives as the input. If I recall correctly, getting this down to about 3 or between 3 and 4 will work pretty well. And we could play around with this stuff. I think these parameters are going to be pretty successful for us. See if ooh, yeah, look at that. We're starting to, that's too much. Max iterate cranked up the number of epochs per fit, and the training started to slow down. So I must have set this at a good level. Okay, so now we're down to 3.8. Let me decrease this a little bit, which is not always a good idea, but if we can creep down a little bit further, yeah. Okay. So yeah, let's try this. So I'll stop the training, and then I will plot it, and then I will change the point size scale as I have been before so that it looks a little prettier. And now what we have here, what I'm actually looking at here is the two-dimensional space. The XY positions of these points are the two-dimensional space that we created at this bottleneck. So in order to create these data points, I am taking the slices PCA dataset. I'm feeding that as input to the neural network here, but I'm telling it to only make predictions to this layer and then give me the output right at that layer. So don't compute any of the rest of it here. And so for each data point that I send in, I'll take one of my data points. It's 130 values. I'll send in the values. I'll do the feed forward process to here, but then once it gets to here, I'll have 2 values corresponding to that data point. And those 2 values, I'm plotting in XY space. And so these are my 1,052 data points represented at this bottleneck as just 2 values. And this space we have here, this is what we can call a latent space. And so what we have here are all of these points. And if I were to click one, what we get is, let me turn down the volume. Yeah. If I click a point here, what we're doing is we're taking that point, we're getting the 2-dimensional position of that point in XY space here. We're taking that 2-dimensional value, we're dropping it into the neural network right here. So we're skipping all this part. We're putting those 2 values in right here and then feeding forward the rest of the way to get back the wavetable that is represented by that point. And so we can do that for any of these points in this latent space, but also I can feed into this part of the neural network here, this latent space layer, any 2-dimensional point, right? So I could feed in this point right here, or this point, or this point, even though there is not a data point in the latent space that is represented in that spot. We can still take those 2 values, that XY position, feed it into the neural network, and get some output. That will be a wavetable. And so what we're hoping is that this will be sort of an interpolated position, some sort of wavetable that the output that we get there will be some sort of interpolation that would exist in the latent space right here, even though we don't have a data point that actually represents that spot of the latent space. So now if I play this, we definitely have that wavetable sound because I'm playing it as a wavetable. So we're going to have the one fundamental pitch unless we change the playback rate of the wavetable. But we can see that we're sort of morphing through these partials that are from the original trombone tones. In some spots, we get some of the lower partials even that make it more trombone-ish. One correlate to this is image generating neural networks like StyleGAN and these sort of things that you'll see these videos of like moving through the latent space and these videos where we're morphing between like different Renaissance paintings or landscape paintings and this sort of thing. This is actually how those algorithms are working as well. They create a latent space and then move around in this space, but instead of projecting back out to wavetables, they're projecting back out to images. And so we're getting those interpolations between those different images and getting those morphings because of the moving around in the latent space and then projecting back to create images.